So let's review the definition of the chain rule. So we should have a pretty good understanding of it, hopefully. And so we have this function, capital F of x, that is a composite function, right? It's a composite of two functions, f and g. So in Leibniz notation, remember he's the guy from Germany, right, that developed calculus at the same time as Sir Isaac Newton was in England. If u is equal to g of x, the inner function, okay, so u is the dependent variable, x is the independent variable. Then when we replace g of x with u, we have f of u, and so y is equal to f of u. Y can be written as a function of u. Okay. Well, if u is equal to g of x, then the derivative of u with respect to x is equal to g prime of x. Okay. And if y is equal to f of u, then the derivative of y with respect to u is equal to f prime of u. And in Leibniz notation, we have the derivative of y up here with respect to x is equal to the derivative of y with respect to u times the derivative of u with respect to x. That's the chain rule for getting the derivative of this composite function. Okay. U is equal to the inner function g of x, so y can be written as f of u. And when you differentiate u and y, right, u with respect to x and y with respect to u, right, we get these two derivatives, and the derivative of y with respect to x is equal to derivative of y with respect to u times derivative of u with respect to x. Now these are not quotients, okay, these are not fractions, but you can think of it as if they were fractions, right? The du's would cancel and you'd be left with dy over dx. You multiply these two fractions. Okay? So it's an easy formula technically to remember because of that. Okay? All right, well we can write the chain rule in prime notation. Or function notation, right? Prime notation or function notation. The derivative of y with respect to x is equal to f, capital F prime of x, right? And the derivative of u with respect to x is equal to g prime of x, right? So we can replace that, du over dx, with g prime of x. Now, the derivative of y with respect to u, right, that's f prime of u. I'm going to leave that blank for just a second. right? And then times the derivative of u with respect to x, we have g prime of x. Now I could put u in there, right, f prime of u, but u is equal to g of x, right? And so instead of putting u here, I'm going to put g of x. So in prime notation, okay, the derivative of big F of x is equal to the derivative of little f evaluated at g of x times g prime of x. Okay. And so this is the chain rule and this is the chain rule, okay, but this is Leibniz's notation, right, and this is prime notation or function notation. Okay. So those are the same, just different notation. All right, so let's do a couple examples. We'll do an example with Leibniz notation and prime notation.
Will we be asked to use one notation or another?
Probably not. Because when we get done today, we're going to have shortcuts on the chain rule. Okay. All right. So in this first example, we're going to find capital F prime of x, right, the derivative of big F of x. If big F of x is equal to the cosine of x squared. Okay. Now I want to remind you something about the parentheses with the trig functions. Okay. You know that we write f of x, right? This is pronounced f of x. F is the name of the function. X is the input variable. Okay. When we write this sine, this is the name of a function, right? This is the name of the sine function. And this is read sine of x, right? This is read f of x. This is read sine of x. But because this is a special function, right, with its own name, sometimes we drop the parentheses. These are the same, right? Sometimes we include parentheses for clarification, sometimes we don't. Okay. The x that goes into the sine function, right, or any function, is called the argument. Okay. So sometimes we put the argument in parentheses and sometimes we don't. Okay. All right. In this case, we're putting the argument going into the cosine function in parentheses. I noticed that on WebAssign. They love parentheses for the argument, put parentheses around the argument. But I often drop them. Okay. So if I didn't have parentheses, it would still be the cosine of x squared. Okay. All right. So this is a composite function, right? We know what the derivative of cosine x is, right? It's minus sine x. But this isn't cosine x, this is cosine x squared. So that's a composite function. The outer function, f of x, is equal to cosine of x. And the inner function, g of x, is x squared. So in Leibniz notation, right, u is equal to g of x. And so in this case, g of x is x squared. And so the derivative of u with respect to x is 2x. y is equal to f of u, right? And so you just replace the x with u, get f of x. And so we have y is equal to cosine u. And you know the derivative of y with respect to u is minus the sine of u. Everybody with me? So the derivative of y with respect to x, which is the derivative of y with respect to u, times the derivative of u with respect to x. Derivative of y with respect to u is minus sine u. Oh, you know, like last week, we were talking about the different forms of differentiation. And I said, you know, in the book, it was just saying, you know, the derivative of. But I said, I was taught to say derivative, right, of y with respect to the variable. Your book now uses that language. Right? They say derivative of y with respect to u, derivative of u with respect to x. Okay. So minus sine u is the derivative of y with respect to u, and the derivative of u with respect to x is 2x. And now we replace u with what it's equal to. It's equal to x squared. And so we have minus. Now this is where I like to rearrange things. I put the 2x in front of the sign, right? And so I have minus 2x times the sine of u, which is the sine of x squared. Okay. So big f prime of x is equal to minus 2x times the sine of x squared. Now putting the 2x out front of the sign, that's just personal preference, so I don't confuse 2x times sine with the sine of x squared times 2x. X squared times 2x, right? It's just clarification purposes. All right, so that's using Leibniz notation, okay? Now let's do it using prime notation. So with prime notation, right, we need to know f prime of x. Well, f prime of x, right, f of x is equal to cosine x. So f prime of x, right, derivative of cosine x is minus sine x. And g prime of x g of x is equal to x squared, so g prime of x is derivative of x squared, which is 2x. And now f prime of x is equal to f prime of g of x times g prime of x, right? That's the chain rule in prime notation. Well, what's g of x equal to? So now we substitute for g of x, okay? And g of x is equal to x squared. So we have f prime of x is equal to f prime of x squared. And g prime of x is equal to 2x. And now we have to evaluate f prime, right, the derivative of f of x, at x squared. So how do you evaluate f prime at x squared? Wherever you see an x in f prime of x, you put x squared. And so f prime of x squared is minus sine of x squared. Minus sine of x squared times 2x. And then this is my own personal preference, but to avoid confusion, I like to put the 2x out in front of the sign. This is my own personal preference, okay? There's nothing that says you have to do it. Okay? So when you do it, when I do it, I get minus 2x times the sine of x squared. And so we got the same derivative using prime notation as Leibniz notation, which you should. Okay, it's just two different kinds of notation. Prime notation seems to be faster than Leibniz notation. Yeah.
Do we need to use both for like tests? And
No. Somebody already asked that. Yeah, you probably won't even use either, to tell you the truth. Okay? Because we're going to be talking about shortcuts. And, you know, it's like the rules of differentiation, right? You know, sum rule, the difference rule, constant multiple function rule, all those, but you don't actually explicitly write them out when you find a derivative. All right. So any questions on that? All right, let's do another. But you've seen like 3 examples now with Leibniz. So I'm just going to use prime notation on this next one. So we're going to find f prime of x if f of x, big F of x. Everybody understands that big F of x and little f of x are different functions, right? Big F and little f, right? It's like big Ed and little ed are not the same person, right? So big F of x is equal to e raised to the x squared minus x power. So we know what the derivative of e to the x is. This is a composite function. Okay. The outer function, right? Remember, we're using our arrangement in our composite function is big F of x is equal to f of g of x, right? That's the arrangement of these. Now you can switch the order of f and g, right? Switch their roles, but I'm sticking with the same roles, okay? So the outer function you can see is e to the x, and the inner function is x squared minus x. So when you were taking your algebra and you learn about composite functions, and you had to decompose a composite function into 2 simpler functions, now you know what you were doing. Okay. All right. So this is the outer function. This is the inner function. So f prime of x, you know, is just e to the x, right? Derivative of e to the x is e to the x. And the derivative of g of x, g prime of x, well, derivative of x squared is 2x. Derivative of minus x is minus 1. So in prime notation, we have big F prime of x is equal to f prime of g of x times g prime of x. So, first step, to evaluate f prime of g of x, replace g of x with what it's equal to. It's equal to x squared minus x. G prime of x, what's it equal to? 2x minus 1. Now, to evaluate f prime of x squared minus x, you just put x squared minus x in for x in f prime of x. And so on the right hand side we have e raised to the x squared minus x power. And then this is times 2x minus 1. Okay. And so you can stop right there if you want. I'll often put the 2x minus 1 in front of the e, just for clarification purposes. Okay. Any questions on that?
So will you explain like the last two lines one more time?
Here?
Yeah.
So this is, right, this is the chain rule in prime notation, right? And so for this function, f of x equals e to x squared minus x, right? We gotta evaluate f prime of g of x times g prime of x. Well, g of x is equal to x squared minus x. So we replace g of x with x squared minus x. And g prime of x is equal to 2x minus 1. So we replace g prime of x with 2x minus 1. Okay. And now, last step, we have to evaluate the derivative of f of x at x squared minus x. What's the derivative of f of x?
Oh, okay.
E to the x. Okay. And so we put x squared minus x in for x here. Then we have e to the x squared minus x. You're welcome. Okay. Any other questions? Okay. All right, so let's make some observations here. So we have f of x is equal to f of g of x. Okay. So, I mean, this is a composite function, right? Big F of x is a composite of f with g. Okay. So big F, or little, excuse me, little f here is called the outer function. And g of x, so parentheses here, right, is the outer function evaluated at the inner function. When we have f of x, right, we say the function f is being evaluated at x, right, the number x. Well, here, the outer function f is being evaluated at the inner function g of x, okay, instead of x. So when we write f prime of x is equal to f prime of g of x times g prime of x. I'm giving myself some space here because I'm going to write underneath this function, right? That's this equality. F prime, right, is the derivative of the outer function okay, and up here, right, in f of g of x, the outer function f is being evaluated at the inner function g of x. Down here, f prime of g of x, right, the derivative of the outer function is being evaluated at the inner function g of x instead of just x. Okay. So it's evaluated at the inner function g of x. Okay. So the first derivative of f of x, f prime of x, is being evaluated at the inner function g of x instead of at x. And then we multiply that by the derivative of the inner function. So this is actually a pattern, right? This is actually a pattern. The derivative big F of x is the derivative of the outer function evaluated at the inner function multiplied by the derivative of the inner function. So you'll notice in using the chain rule, we work from the outside to the inside. And you may notice that in this pattern over here, right? We differentiated the outer function, evaluated it at the inner function, and then we multiplied that by the inner function, the derivative of the inner function. Right? We start from the outside and we work in. Okay? So, as an example, we're going to find the derivative of y with respect to x given y is equal to the sine of x squared plus 2x plus 1. Okay. So the sine function is the outer function, okay? And this quadratic, x squared plus 2x plus 1, is the inner function. Right? The sine function contains the inner function. Okay? The sine function contains the quadratic. So the derivative of y with respect to x is equal to the derivative of sine x squared plus 2x plus 1. Well, what does our pattern over here tell us? We take the derivative of the outer function and evaluate it at the inner function. Well, the derivative, sine is the outer function. The derivative of the sine function is the cosine function. And then we evaluate that at the inner function. What's the inner function? X squared plus 2x plus 1. And then we multiply that by the derivative of the inner function. What's the inner function in this case? X squared plus 2x plus 1. Okay, we start from the outside and we work in. So we take the derivative of the outer function. Derivative of sine is cosine. and we evaluate the cosine function at the inner function, which is x squared plus 2x plus 1. And then we multiply that by the derivative of the inner function. Derivative of x squared plus 2x plus 1. Well, what's the derivative of x squared plus 2x plus 1? Derivative of x squared is 2x. Derivative of 2x is 2. And this is where I like to do this. Right? You can leave the answer in that the way it is. But this is why I like it. Is the argument going into cosine the product of these two? Or just this guy right here? That's why I like to put this stuff like up in front of the cosine. It clarifies. It clarifies that 2x plus 2 is not part of the argument going into the cosine. So just to remind you, right, the derivative of sine is cosine, right? That's where that came from. In case you haven't done the homework yet. Okay. All right, any questions on that, ladies and gentlemen? Okay. All right, so now we're going to come up with some shortcuts. So you don't have to write out Leibniz or prime notation all the time. All right, so you remember the power rule. From, I think we did that back in section 3.1. Okay. N is any real number. Then the derivative with respect to x, derivative of x to the n with respect to x, you know, is just n times x to the n minus 1 power. You should already have that in your notes from section 3.1. Okay. Now we're going to define what we call the general power rule. We're going to replace x with a function of x. Okay. So n is any real number. And g of x is a differentiable function. G of x is differentiable. Then the derivative with respect to x of g of x raised to the nth power. All right, so we're replacing x here with a function of x. Okay, so g of x is the inner function, x to the n is the outer function. Okay. And by the chain rule, that derivative is equal to n times g of x to the n minus 1 power. So this is the outer function evaluated at the inner function. Or this is the derivative of the outer function, excuse me. Derivative of the outer function evaluated at the inner function. And now we're going to multiply that times the derivative of the inner function, which is g prime of x. That's the general power rule. Okay. Any questions on that? So you can show this using Leibniz notation or Planck notation. Okay. So let's do an example. We're going to find the derivative of y with respect to x if y is equal to the square root of x squared minus 5x plus 1. Well, we know how to find the derivative of square root of x, right? Square root of x is just x to the 1/2. But that's not square root of x, right? That's the square root of a function of x. Okay? So this is equal to x squared minus 5x plus 1 raised to the 1/2 power, right? So the outer function, this is a composite function. The outer function is x to the 1/2, and the inner function is what's in parentheses. So the derivative of y with respect to x using the general power rule, you bring the exponent 1/2 down in front of the left parentheses. Multiply that by the inner function, raised to the 1/2 minus 1 power. Right? You subtract 1 from the exponent. So that's the first part here, right? And now we got to multiply that by the derivative of the inner function, which is x squared minus 5x plus 1. And so the derivative of x squared minus 5x plus 1, derivative of x squared is 2x. Derivative of minus 5x is minus 5, and you know derivative of a constant is 0. And so that's the derivative of our original function. Square root of x squared minus 5x plus 1. Any questions on that? Yes, ma'am.
Will we have to simplify that?
You know, on the exam, you'll have a whole bunch of functions you have to differentiate, and almost certainly you will not have to simplify. Okay? You'll do one pass and then stop. Okay? Now, if you have to find the equation of a tangent line, it might behoove you to simplify. Right? Because to find the equation of a tangent line, you got to know the slope, right? And it might be, you know, it may not be worth trouble simplifying it, right? You just put in whatever the value of x is and do the arithmetic. Yeah. All right, let's do another. We're going to find f prime of x if f of x is equal to 2x minus 3 to the 4th power times x squared plus x plus 1 to the 5th power So before we start talking about the chain rule, okay, general power rule, what rule do we have to apply in finding this derivative? Product rule, right? And remember, there are like 8 different expressions for the product rule, right? So you pick the one that works for you. And so the one that I use, right? Remember, I like to break this up into, this is the first function, this is the second function. Okay. And the form I used was derivative of the first times the second plus the derivative of the second times the first. Okay. All right. So derivative of the first function, right? We use the general power rule. Bring the exponent 4 down front of the left parentheses. Subtract 1 from the exponent. And then multiply that by the derivative of what's inside. And the derivative 2x is 2, derivative minus 3 is 0. So the derivative of what's inside is just 2. And then we have to multiply that by the second function. So it's times x squared plus x plus 1 to the 5th. Okay. So this is f prime, right? This is the first function, derivative of the first function, and then multiplied by the second function. Okay. Then we add to that the derivative of the second function. And again, we apply the general power rule. Right, we're going to bring the 5 down front of the left parentheses, subtract 1 from the exponent, okay, and then multiply that by the derivative of what's inside. So we have 5 times x squared plus x plus 1 to the 4th times the derivative of what's inside. Derivative of x squared is 2x. Derivative plus x is plus 1. Derivative plus 1 is 0. So that is the derivative of the second function. And now we've got to multiply that by the first function, which is 2x minus 3 to the 4th. And so if this was an exam question, stop right there. Okay. Just want you to know if you know how to find the derivative. We'll save the algebra for when it's more important times.
Sorry to ask you to repeat yourself, but why is there that loose 2 in the F prime section?
Hold on. It's okay to ask me to repeat myself, because I do it all the time when I'm alone. But okay, no. What was your question?
So in the solution, above the F prime area, there's a 2 in both sides. Where did that come from?
So, finding this derivative, right? So we brought the 4 down front, subtracted 1 from the exponent. And then we got to multiply that by the derivative of what's inside.
We got to multiply what by the derivative?
We got to, right? This 4 times 2x minus 3 cubed, we have to multiply it by the derivative of what's inside parentheses here.
Okay.
And the derivative of 2x is 2. Derivative minus 3 is 0. So the derivative of 2x minus 3 is just 2. Okay? That's the G prime of x. Okay?
Professor,
Yes, ma'am.
does it work? So you applied the power rule, the general power rule, and the product rule at the same time, kind of. Can you do it separately, or does it get too confusing?
Separately.
Like first you do the product rule, then you do the general power, or does that not work?
Well, I mean, you technically, I guess you could have wrote this out as the derivative of this, d over
Yeah.
dx times this, right?
Mhm.
Plus d over dx of this times that. Now you could, right? That
Yeah.
would be the product rule.
Yeah.
And then fill in the derivatives.
Okay.
You could technically do that, but you're gonna end up, we
Okay.
did 2 steps at once, basically.
Okay.
Okay.
And those steps were to pass the product rule and general power.
Yeah. So we use the product rule. And general power rule. Concurrently. I think that's the right word. Right? Concurrently.
Sounds good.
Right? You gotta use them both at, right? You're using them both at the same time. I mean, this is my version of the product rule. F prime, right? First derivative first function times the second function, plus derivative second function times the first. And I filled in for the first derivative of the first function and derivative second function while I was writing that out. So it's that you're doing two things at once. You'll get, don't worry, you'll get plenty of practice with the homework. Okay. You're just learning the rules here. You get good at this doing the homework. Right? This is what I used to do after dinner. I used to go up to my dorm room and I just loved doing this stuff. Yeah. Some of us didn't have a life. Okay. Then I had to break out the physics book. Hated that. Alright, so any questions on the general power rule? Alright, so now let's go back and talk about the derivative of the natural exponential function. Which you already know, because we've used it already. Alright, so the derivative with respect to x of e to the x, easiest derivative of them all, probably, apart from the constant function, right? Apart from the derivative of the constant. Well, now let's apply the chain rule to this. We're going to replace x with a function of x. So we have the derivative with respect to x of e raised to the g of x power. So this derivative is equal to a product. Just as, so the first factor, just as derivative e to the x dx, the first factor in this derivative is e to the g of x power. So with the chain rule, right, derivative of the natural exponential function is itself. And then what do you think we have to multiply this by? G prime of x, derivative of the inner function. So let's do an example. We're going to find f prime of x if f of x is equal to e raised to the tangent x power. This is a composite function. What's the outer function? E to the x. What's the inner function? Tangent x, right? Alright. So f prime of x, from our formula over here, e raised to a function of x, the first factor, is itself. So the derivative of e to the tangent x is e to the tangent x times the derivative of tangent x, right? I'll write it out. Derivative of tangent x. Now you don't have to write this out on an exam, but I'm just showing you where it's coming from. What's the derivative of tangent x? Secant squared x. So f prime of x is equal to e raised to the tangent x times secant squared x. And again, right, I often like to put the secant squared x in front of the e, right, just to make it more readable. Any questions on that? Okay. All right. So now let's talk about the derivative of any exponential function. Okay. Remember in pre-calculus we studied exponential functions, didn't we? An entire chapter on it and logarithms. So an exponential function, right, is of the form a to the x, where a is greater than 0 and not equal to 1. Because if a equals 1, you got 1 to the x is just equal to 1. That's not an exponential function. But if a is any positive number not equal to 1, then a to the x is an exponential function. What's the derivative of that equal to? Well, you can't bring the x down front and subtract 1 from the x. Can't do that. Right? So the derivative, your textbook does a very good job of showing this. Okay? But the derivative of a to the x, well, you know the derivative of e to the x is just e to the x. So you might be tempted to say, well, the derivative of a to the x is just a to the x. That's half correct. Okay. Just like derivative of e to the x, e to the x, you're half correct. You say derivative of a to the x, expect that a to the x. But we have to multiply that by the natural log of the number a. Okay. I wish I'd written this over here. So what's the derivative when x is replaced with a function of x? When we have a, instead of a being raised to the x power, a is raised to a function of x. What's the derivative of that? Well, the pattern is the first two factors are the same, or the pattern's the same. this is equal to a raised to the g of x power times the natural log of a. What do you think we're missing? What's the last thing we've been doing? G prime of x, right? That's the pattern, right? You're gonna multiply that by the derivative of the inner function. Okay. So let's differentiate. Do some examples, each function. So in the first one, we have f of x is equal to 2 raised to the x power. So if f of x is equal to 2 to the x power, what's f prime of x equal to? Looking over there in the box. A is equal to 2 in this case, right? So the derivative of 2 to the x is going to be, yep, 2 to the x times the natural log of 2. Right? We just put 2 in for a over here, and we have the derivative with respect to x of 2 to the x is equal to 2 to the x times the natural log of 2. Okay. Thought I heard something. No. Next we have h of x is equal to 3 raised to the x squared minus x power. Now you got to use the pattern up here, right? A is equal to 3, and g of x is equal to x squared minus x, right? So the derivative of 3, maybe I'll write it out. The derivative of 3 raised to the x squared minus x power. A is equal to 3, g of x is equal to x squared minus x. So h prime of x is equal to 3 raised to the x squared minus x power times the natural log of 3 times the derivative of the inner function, x squared minus x. With respect to x, the derivative of x squared is 2x, and the derivative of x is 1. So derivative of x squared minus x is 2x minus 1. Any questions on that? All right. Guess my notes are just about right. So, question. Why is it called a chain rule? And before we do an example, right, in what we've been doing, we have an inner function and an outer function, right? A function inside a function. But with composite functions, you can have a function inside a function, and those inside another function, and all that inside of another function, and all that inside of another function. And so every time you have that inside of another function, you add one more link to the chain in the differentiation of that function. Okay, and that's why it's called the chain rule. Okay. It's like another link in the chain. Okay. So we're going to demonstrate this. We're going to differentiate f of x is equal to the square root of sine of x is the square root of the sine of e to the x. How many functions are there in that composite? There's three. There's the square root function, there's the sine function, there's the natural exponential function. So the natural exponential function is a function inside the sine function, and the sine function in turn is inside the square root function. Okay? So we got a function inside a function, and those two are inside another function. Okay? So this chain has three links in it. Okay? All right, and so we got to differentiate this. Well, you know, square root means 1/2 power. So this can be written as the sine of e to the x raised to the 1/2 power, right? So when we differentiate to get f prime of x, in our first pass, sine of e to the x is the inner function in this case, right? And what rule, in our first pass at differentiation, what rule do we apply? The general power rule, right? This is like x to the 1/2 power, right? So when we do the general power rule, first pass, right? We bring the exponent 1/2 down front. That's times the inner function raised to the 1/2 minus 1 power, which is minus 1/2, right? And now we got to multiply that by this inner function, or by the derivative of that inner function. So this is derivative with respect to x of the sine of e to the x. Okay. So this is done. We just keep carrying this part along. But now in this derivative, what's the outer function? Sine is the outer function, and e to the x is the inner function, right? In this derivative. So sine is outer, e to the x is inner. So f prime of x is equal to 1/2 times the sine of e to the x raised to the minus 1/2. What's the derivative of the sine function? Cosine, right? So derivative of sine e to the x with respect to x is equal to the cosine of the inner function e to the x times the derivative, I wrote e to the x here, and then inner. E to the x is the inner function. Right? So we have cosine of e to the x times the derivative of the inner function e to the x. And the derivative of e to the x with respect to x is just e to the x. Actually, let me write it this way. So it's cosine e to the x times the derivative with respect to x of e to the x, right? So we take derivative of the outer function. So we have derivative of sine is cosine, and then we got to multiply that by the derivative of the inner function. The inner function in this case is e to the x. And then When you take derivative e to the x with respect to x, you just get e to the x. You wouldn't have to write this out this many times on an exam, right? You might be able to go from here to here, right? Because you would you go from here to here, you would say, okay, differentiate 1/2 times sine e to the x raised to the minus 1/2. And now you're gonna multiply that by the derivative of this inside the bracket. Well, derivative of sine e to the x is cosine e to the x times the derivative of e to the x, which is e to the x. Right? And you're done. So I wrote everything out in 3 steps. You could do it in 1, right? On the exam. Okay. All right. So any questions on that, ladies and gentlemen? All right, 128. Let me see who's not here.